This is section 1.2, which is function behavior. This also ties into the AP standards 1.1 and 1.2, which are change in tandem and rate of change. So the first thing we need to review is what a function is. So a function maps every input, or x, to one output, or y. And you think back to Algebra 1, where you learned the vertical line test. So the vertical line test can tell us on a graph if something is a function. The other part is domain and range. So domain is our inputs, or our x values, and range is our outputs, or our y values. So we're going to look at two quick examples. One is an equation and one is a graph. So if we're looking at the equation, we have to think about, domain, the things I always remind students to look out for on domain from an equation. So the two types that you're going to encounter are fractions. And we have to remember with a fraction, we can't have 0 in the denominator, and square roots. And with a square root, we can't have a negative value underneath that square root. So this example that we're looking at right here, we have a square root. So we know that we have to have x plus 3 needs to be greater than or equal to 0 in order to make that function defined. So if we solve this, we know that x has to be greater than or equal to -3. So just to kind of review interval notation, we would say that the domain, we would use square brackets and say -3 to infinity. And we always use parentheses with infinity because infinity is not a number, we can't reach it. But we use those square brackets on the -3 because it's greater than or equal to -3, because we can take the square root of 0. Okay, and then if we think about our range, so our range of this function from the equation, if we plug in -3, we get 0. If we plug in numbers bigger than -3, our numbers are going to keep increasing. So that tells us that our range, again, square brackets, 0 to infinity. Okay, so that would be our domain and range for the equation. Now, if we look at the example that is the graph, you can see we have open circles and closed circles on this graph. So from the graph, our domain, we're looking left to right. So our furthest left point is at -2, and it's an open circle, so we're going to use parentheses, -2, and then our furthest right point is right there at the 4, and it's a closed dot, so we're going to use square brackets. And then our range, this sometimes confuses students because there's not a dot, like there is a dot, but it's not an actual visible dot at the lowest point, but our graph is defined at that point. So we don't have a hole, we don't have an open circle. So that means our lowest point is at -2, and it can be -2. So we're going to use square brackets, -2, and then our highest value is at 3, also square brackets. Okay. So next we're just going to kind of do a quick review of key features of a graph. So if something is increasing, it means it's headed upward from left to right. Decreasing, we're going down, and constant means it is a horizontal line. Okay, concave up. So concavity might be a new topic. We're going to talk a lot about it this year in AP Precalc. But concave up is where it's curved. It's like kind of like a bowl, an upside down umbrella. Concave down would be your umbrella. Okay, and then an inflection point is the point where we switch concavity. So going from concave up to concave down, or from concave down to concave up. That is our inflection point. Okay, the next topic is boundedness. So boundedness talks about whether or not our graph can go up forever or down forever. So the first one we're going to look at is bounded below. So that would be something like this. So you can see that this graph clearly has a minimum value, but it doesn't have a maximum. Those arrows show it's going to go up forever. So this one is bounded below. We have a bound at the lowest point, but we don't have a bound at the highest point. Bounded above is going to be the opposite of that, maybe like this upside down parabola. So there's a high point, a maximum point, but it's going to keep going forever to the negative. Unbounded. So unbounded might be something like this hyperbola, because we can see on the hyperbola, the arrows are showing it's going to keep going up forever, it's going to keep going down forever. So that would be unbounded. And then bounded would be, think like a sine or a cosine function, where it's never going to go above 1 or down below -1. It's going to stay within those bounds. Okay, more remembering of past material. Local extrema. So local extrema talk about our relative maxes and our relative mins. So we can have global maxes and global mins, which would be the overall highest or lowest point. And then we can have local maxes and local mins, which are just relative. Another way you might hear it, you might hear relative maxes or relative mins. They're relative to the points around it. So for example, this point and this point would both be local or relative maximums. And that point right there would be a relative or local minimum. Even though this doesn't have arrows on it, but we know it's going to keep going down forever. So this graph would not have a global minimum, but it does have a local minimum. And this graph also, so this point right here, we could call a local max, and we could also call that specific point the global max. Okay, symmetry. So we've talked about symmetry before. Even symmetry. So if my function is even, that means that my graph has symmetry about the y-axis. So any function that we have that has symmetry about that y-axis, that tells us it's an even function. Symmetry, so odd functions have symmetry about the origin. A trick I like to talk about is if you can flip the graph upside down. So if you're looking at it on a graphing calculator or even just a sketch of something, if you flip that upside down, does it look the same as it did originally? So that would mean that it's odd and it has symmetry about the origin. Neither could be something like this that doesn't have symmetry about the y-axis and it doesn't have symmetry about the origin. Okay, continuity. So continuity has to do with whether or not our function is continuous at all points. So the first graph we're going to look at is just a continuous graph. So those are the graphs you're probably used to seeing. No holes, no breaks. It's just a continuous graph. Okay, then we have what's called a removable discontinuity. So a removable discontinuity, think of it as if you can plug a hole and have it become continuous, that's a removable discontinuity. So if we think of a similar graph here, but I have a hole along the way. So that open circle mid-graph, if I put a point right there at that hole, my graph would become continuous. So that's what we call a removable discontinuity. Now, the opposite of that would be a non-removable discontinuity, which we're going to look at two examples here. So a non-removable discontinuity might, lost my picture here, might be something like this, where you can see there's a jump in the graph. So this is considered a jump, where my graph stops at one point and then it picks up at another point. Another type of removable discontinuity would be something like a hyperbola. And we call that an infinite. So that's an infinite graph. So there's no way for either of those graphs we could just make it continuous by putting a dot in one spot. So that's what we call a non-removable discontinuity. Okay, So our last, not our last example, but kind of putting all this together. So talking about the different intervals where this is increasing, decreasing, concave up, and concave down. So if we start with increasing, we're looking for our graph to be going up from the left to the right. So I just start here on the left, start here, and I work this way. And when I list the intervals of increasing, decreasing, or concave up, concave down, I'm just listing the x values. So I'm starting with my graph at the furthest left point, which is at -4 right here. And I'm just listing x values as I go from left to right. So if I follow along from -4 down to -2, I am decreasing. So I could put that in my list here. So if I write here from -4 to -2, I'm decreasing. I'm using parentheses and not square brackets because we're not talking about a single point. We are talking about an interval. So we're decreasing from -4 to -2. At -2, I start to increase. So -2, I'm increasing until I get to 0. So again, I'm talking about x's. So now we're right here at 0. Then I start decreasing again from 0 to 4. That's where I start to decrease. And then I'm increasing from 4 to 7. So that would be my increasing and decreasing. So now, if we look at concavity, I'm still listing my x's. So concavity, I'm looking for kind of like either a bowl or an umbrella shape. So if we look for concave up, we can tell that this portion right here of my graph is going to be concave up. So we can see from 2 to 7, my graph is concave up. And then this section right here is concave down. So from -2 to +2, my graph is concave down. Okay, so now we're on to kind of that 1.2 part of the AP standard, and we're talking about average rate of change. So average rate of change, I always say, is just a fancy way of saying slope, finding slope. So just to remind you of our slope formula, it's going to be y2 minus y1 over x2 minus x1. So that is really easy to do on a graph. We're not always going to be given a graph. So we want to know how to find the slope both algebraically from an equation, but we also can look at graphs. I put this little helpful hint up here. If you're given an equation, you have options. You can graph it on a calculator. You can use the table feature on a calculator. So you can input it into y equals, use the table feature to find the different values. You could also just plug in values for x and y. So these are all options for you. So the first one we're going to look at is on a graph. So the graph is already provided for us, and it says to find the average rate of change on the interval -3 to 3. So again, I want you to remember that those numbers, the -3 and the 3, they're both x values. So if we go to -3 and find where that is on our graph, that's that point right there. And if I go to +3, it's that point right there. So basically all I'm doing is I'm counting the slope, the rise over the run between those 2 points. So if I go from here, and then over, so I'm going up 1, 2, 3, 4, 5. And I'm going over 1, 2, 3, 4, 5, 6. So my average rate of change on the interval -3 to 3 would be 5, 6. Simple as that. Okay, now let's look at what we do if we have an equation. So for this equation, I have -x to the third minus 3x on the interval -2 to -1. So all I'm doing is the same thing as what we did over on the left, except I'm thinking about, okay, I'm trying to find the slope between 2 points. I don't have a visual though, but I do know this is my x1 and this is my x2. So I'm going to put -2 and -1. We're trying to find the y coordinates. That's where we need to start. We need to find the y coordinates of each of these points. So if I plug in -2 negative 2 cubed. So that right now I'm finding f of negative 2. So negative 2 cubed minus 3 times negative 2, I get 2. Oop, that didn't write. I get 2. Okay, if I find f of negative 1, I'm finding negative 1 cubed minus 3 times negative 1, and I get negative 2. So I just found 2 points. We know how to find the slope between 2 points. We're taking our y2 minus our y1, so negative 2 minus 2 over our x2 minus x1. So that would give me negative 4 over 1. So my average rate of change is negative 4. Okay, so instantaneous rate of change. So even though we're not dealing with lines, we're dealing with curves, the instantaneous rate of change is the average rate of change, or what we just said is like slopes over smaller and smaller intervals. So think of a graph, we're zooming in to make it smaller and smaller intervals so they look like lines. So we're finding the slopes of all the different lines, or the tangent lines to our graph. And so we're going to combine this kind of with this idea of concavity. And so what we're looking at is if we have a positive rate of change. So a positive rate of change means that the function is increasing. So you can think of a positive slope. So if our line is going upwards, we have a positive rate of change. If our rate of change is negative, that means our function is decreasing. So we have a negative slope. So then if we say the rate of change is increasing, so now we're not talking about the function, we're talking about the rate of change. So the slopes are getting bigger. So a rate of change increasing could look like this. Oops. Could look like this. That's a bad line. Let's try that again. Okay, could look like that. It could also look like this, and this is the one that confuses people because it looks like the graph is going down, but what you have to think about is right here we maybe have a slope of negative 4, and right here we have a slope of negative 1/3. So if I go from negative 4 to negative 1/3, my slopes are actually getting bigger. They're getting less negative. So that's where this gets really confusing, but what we're trying to think of is increasing rate of change means that this is going to be concave up. So if we have an increasing rate of change, it's concave up. If our rate of change is decreasing, so that's the slopes getting smaller, we're going to have something like this or like this. Now, and so it's going to be concave down. So eventually, like what I think about is when I see rate of change decreasing, I see that D, and that helps me connect with concave down. So I think concave down, the average rate of change is decreasing. But I also, my brain, I like to put numbers in for the slopes. So like our illustrations down here, we can see that this would be, the slopes are getting bigger. So we know that this is going to be concave up, which means our rate of change is increasing. But if we're just talking about the function itself, the function is also increasing. So we would say that this graph is increasing at an increasing rate. Now, this graph is going down, so it's decreasing. The function is decreasing. It is concave up as well. Okay, so it's concave up. And our rate of change is still increasing. And that's where we talked about right up here with these weird slopes. So this is the rate of change is increasing because it's getting less negative as we go from left to right. So this one is decreasing, this function is decreasing at an increasing rate. So that's where the language gets really technical and kind of confusing. But we'll practice this a lot this year. Okay, and that is it.